Let's move on to our next speaker, who is Sergio Mazzola, who is a PhD student from ETH Zürich in the PULP group.
Thank you. Good morning, everybody. It's great to be here. Okay, so today I want to tell you about MemPool flavors. So I'm sure you heard a lot these days about how today's large workloads require massive computational powers that directly translates into the need of hundreds of cores and large memories. A common approach to this is the shared memory cluster, which guarantees high level of flexibility and parallelism. For those of you already familiar with some past work of our group, Okami is an example of how we increase the number of cores by scale out, so instantiating multiple clusters. But today I want to tell you about scale up, so enlarging the single cluster. And there are a few good reasons to do this. Without multi-cluster, we reduce the overhead of having to split and data chunks and transfer them over the multiple clusters, so we can have a higher compute utilization. And also a single cluster is easier to program. But still with this scaled-up system, we have to still grant low latency access to the large memory system, and we have to be careful to keep all of this physically implementable. So that's quite challenging. Let's see how do people actually do it. And an example is the Google Tensor Processing Unit, which can scale up to 65,000 processing elements by relying on massive specialization just for systolic workloads. When we move a bit more towards versatility, we have the example of GPUs, like the NVIDIA Hopper GPU, that can scale up to 128 cores per streaming multiprocessor. But GPUs generally still rely on a single instruction, multiple thread paradigm. So when we go on the complete other end of the versatility spectrum, we have general purpose CPUs, like the AMD EPYC series, that can scale up to 16 cores per die. And these are fully general purpose systems, so they have complex cache hierarchies and additional logic that makes them poorly scalable. So with MemPool, we want to keep the same level of versatility, but increase the number of cores in the single cluster to hundreds or thousands. But MemPool is not only an architectural solution to this, because it's a very active project. We have a very lively GitHub repository with many, many contributors. And over the years, this brought to the development of many architectural variants of MemPool that cover a large trade-off between versatility and performance. We have vectorial workload acceleration, we have transformer acceleration, we have systolic variants. We are researching into scaling MemPool up to thousands of cores and using network on chips and also cache-based system. But MemPool is also more than this. Because around all this hardware, we built, give it a bit of time. So yeah, we built a large software kernel library, and we have support for several runtimes, and also for both GCC and the LLVM compilation, and for several platform emulators. Also on the physical implementation side of things, we have mature backend flow in many modern technologies, and we have already 2 tape-outs. And the latest of them is Hardstream, which was freshly taped out last year, and it implements 64 cores of MemPool in Global Foundry's 12-nanometer technology. But today, I want to dive with you into the architecture of 3 architectural flavors of MemPool: the baseline, the systolic, and the vectorial one. So let's check out baseline MemPool. MemPool can scale to hundreds of cores thanks to the hierarchical architecture it has. And it is based on the unit of repetition of the MemPool tile. A MemPool tile contains 4 RISC-V cores. These cores are 32-bit snitch cores, which is a very lean and small area occupation core, fully open source, of course. And it's very modular and easily extensible with other ISA extensions. In the MemPool implementation, each core has an independent instruction flow. So each one of the 256 cores can be programmed independently. And another nice feature of Snitch is that it's designed to be latency tolerant. So in such large memory system, we can tolerate the bubbles coming from the interconnect very easily. Then in the mempool tile, we have 16 memory banks. And in the same tile, a core can access each bank in just one cycle of latency. Then when we move to the higher hierarchy level, we have the mempool group that instantiates 16 tiles. And a core in the group can access all the other banks in just 3 cycles of latency. When we move even higher to the cluster, we have 4 mempool groups, and a core here can access every other bank in at most 5 cycles of latency. So as you can imagine, the physical implementation of all these interconnects can be quite challenging, and we tackle these with a physical-aware design from the very early stages. And physical implementation of mempool is so interesting that other researchers are using mempool as a benchmark for their EDA tools. For example, NVIDIA tried to benchmark their artificial intelligence-based floor planning algorithm with our mempool RTL. And you will find many more architectural details of mempool in our journals on transaction computers. But let's take a look at systolic mempool now. So the idea here is that we want to leverage the regular data flow of systolic workloads to accelerate them, but still keep the flexibility of a shared memory system. For example, take a pure, simple systolic array where processing elements are connected in a 2D neighborhood-based mesh. And we want to map this topology on our cluster. So, for example, we can think about implementing the functionality of the processing elements on our general-purpose cores. And then we can make the cores exchange data in a systolic fashion through the cluster interconnect that can connect all the cores. And we store this data in memory mapped queues in the cluster banks. We can do this efficiently in mempool thanks to some lightweight ISA extension. And the first one of them is a queue manager that we implement in hardware for every memory bank that allows every core to access all the memory mapped queues in just one instruction. So we get rid of all the overhead that would be required for FIFOs, head and tail pointers. Moreover, we implement within the cores some logic to automatically refill the register file of the cores with the data from the memory mapped queues. And this actually cancels every need for load and store operations and actually implements a systolic autonomous data flow. So like this, we can implement efficiently any systolic topology in our cluster, which is also dynamically reconfigurable at runtime. And you will find many more details about this in our journal on transaction on VLSI. And by the way, this is the architecture that ended up in our Hardstream chip. So let's take a look at Vectorial MemPool now. And the idea here is that we want to fight the von Neumann bottleneck by trading off a larger L0 size to loosen the requirement for the bandwidth towards L1. This is why having a larger L0 allows us to have higher data reuse closer to the functional units in the cores. But if you think about it, the data L0 is nothing else than the core's register file. And in a scalar architecture, the register file is not a knob that you can tune. But in the Vectorial architecture, the register file is flexible by design. So what we do is we leave just one niche core in a mempool tile, and we implement SPATS. SPATS is our short vector machine that is based on the RISC-V vectorial extension, and it has a parameterizable number of lanes. Every lane implements a vectorial floating point unit, and it has a dedicated memory port. So in total, we have 64 cores and 256 vectorial floating point units. And you will find many more details about SPATS in our journal on TCAD. So now let's do a bit of flavor tasting, or in a bit more boring way, the results section. I showed you all these flavors, but eventually, which one do we pick? And to try to answer this question, I will use the usual Matmul, but for a very good reason. Matmul is a high compute intensity kernel, and we have it optimized for all of these mempool flavors, because it's very common in our target applications, like machine learning, digital signal processing. So let's take a look at the utilization. We have 256 floating point units in all of these mempool flavors. So ideally, we want to perform 256 MAC operations at every cycle. But if you consider a trivial implementation of Matmul, you can make a MAC only after 2 load operations. So these account roughly for just 33% utilization. So when you think about it, the baseline mempool already improves quite a lot on that, thanks to the general purpose capabilities of the cores and the data reuse they can have, and to the mempool hierarchical architecture. But Systolic is able to go even 7% faster thanks to the Systolic autonomous data flow, and Vectorial can improve on that of a further 60% thanks to the reduced bandwidth towards L1. But so what flavor do we pick? And the answer is still that it depends on what you want. And to explain this, let's take a look at the mempool tile area. As you can see here, we can swing across the several mempool flavors without too much area overhead. But the trade-off is really clear when we look at the area breakdown, because we realize that, for example, the vectorial flavor spends much less hardware on the versatility functionalities of mempool, because we have only one general-purpose core per each tile. So if we want to accelerate vectorial workloads, vectorial flavor is perfect, but we are going to lose generality for other workloads. But then if you want versatility, we can go back to mempool baseline, or if we want to accelerate also systolic workloads at a small area cost, we can go to the systolic flavor. And this is how we realize our large cloud of trade-off between versatility and performance. And by the way, these are only 3 of the flavors. I have 4 more in the previous slides that I can go on talking about for hours, but I'm going to stop here for today. So yes, mempool is a de facto research platform. It's fully RISC-V-based and open source. Our scaled-up clusters cover a large trade-off space from classic shared memory systems to exotic architectures, but always with an eye on versatility and programmability. And it's been a very lively ecosystem for 5 years now. We have multiple tape-outs and many, many publications. So yeah, you will find here our GitHub repository, our contacts, and we also have a booth upstairs. So if you didn't visit yet, feel free to swing by. And I think this is all I wanted to tell you today.
Thanks a lot, Sergio. Is there any question for our speaker? I guess not, so let's thank him again.
Thank you.